Philadelphia, Pennsylvania. February 1946. A crowd of journalists, military officials, and scientists gathers in a basement laboratory at the University of Pennsylvania. They have been invited to witness something that, until now, most of them would have considered impossible. At the front of the room stands a machine unlike anything the world has ever seen. It stretches across an entire wall. It stretches across every wall. It fills the room. 18,000 glass tubes glow with a soft amber light. Hundreds of cables snake across panels of switches and dials. The heat is extraordinary. The noise is constant. And then, the machine is switched on. In the time it takes a human to draw a single breath, Eniac solves a mathematical problem that would take a trained mathematician 10 hours to complete by hand. The room falls silent. And then it erupts. The computer age has begun. Welcome to Bit by Bit. This is the story of ENIAC. Part 1. The problem that built a machine. To understand why ENIAC was built, you need to understand one thing about World War II. It was, among other things, a war of mathematics. Every artillery shell fired from every gun had to follow a precise trajectory through the air. That trajectory depended on dozens of variables: the weight of the shell, the angle of the barrel, the speed of the wind, the temperature of the air, the rotation of the earth itself. To hit a target, soldiers needed firing tables, booklets of pre-calculated numbers that told a gunner exactly how to aim given any combination of conditions. A single firing table required roughly 3,000 separate calculations. And the US Army needed hundreds of firing tables, for dozens of different weapons, constantly updated as new guns were developed. The Army employed over 200 human mathematicians to do this work. They were called computers, because that was what the word meant in 1942. A computer was a person who computed. Even with 200 people working in shifts, the Army was falling behind. New weapons were reaching the battlefield faster than the tables could be calculated. Soldiers were firing guns without proper guidance. Shells were landing in the wrong places. Something had to change. In 1943, the Army approached the University of Pennsylvania with a proposal. Two engineers, John Mauchly and J. Presper Eckert, had been working on an idea for an electronic calculating machine. The Army agreed to fund it. The contract was signed. And the project that would change the world was given a name: the Electronic Numerical Integrator and Computer. ENIAC. Part TWO. Building the Impossible. John Mauchly was a physicist who had spent years frustrated by the slowness of hand calculation. He had been studying weather patterns and believed that if he could calculate fast enough, he might be able to predict the weather days in advance. But the mathematics was simply too slow to do by hand. J. Presper Eckert was an engineer, 12 years younger than Mauchly, meticulous and brilliant. Where Mauchly had the vision, Eckert had the practical genius to make it real. Together, they faced a problem that no one had ever solved before. How do you build a machine that can calculate electronically, at speed, without breaking down every few minutes? The answer, at the time, was the vacuum tube. A small glass cylinder, about the size of a human thumb, that could switch an electrical signal on or off, representing, in the language of mathematics, a 1 or a 0. The vacuum tube was already used in radios and early electronics. But no one had ever tried to build a calculating machine using thousands of them. The reason was simple. Vacuum tubes failed constantly. They burned out like light bulbs. A machine with 100 vacuum tubes might have one fail every few hours. A machine with 18,000 vacuum tubes would, by simple probability, have one fail every few minutes. Eckert solved this problem with a combination of engineering and obsession. He ran the tubes at far lower voltages than they were designed for, reducing the heat and stress that caused them to fail. He designed custom circuits that were gentler on the components. And he established a maintenance regime so rigorous that teams of engineers monitored ENIAC around the clock, replacing tubes before they could fail rather than after. It worked. Not perfectly. ENIAC still broke down regularly. But it worked well enough. Construction began in 1943 and took nearly 3 years. The machine grew to fill a room 45 feet long and 30 feet wide. It weighed 30 tons. It consumed 150 kilowatts of electricity, enough to power a small neighborhood. When it was running at full capacity, the lights in nearby buildings dimmed. And it contained not just 18,000 vacuum tubes, but also 70,000 resistors, 10,000 capacitors, and 6,000 switches. Every component was wired by hand. Part 3. How Eniac actually worked. Eniac was not a computer in the way we think of computers today. It had no keyboard. It had no screen. It had no permanent memory in the modern sense. And it had no software, not in any form we would recognize. To give Eniac a problem to solve, engineers had to physically reconfigure the machine. They plugged cables into panels, like a telephone switchboard, connecting different units of the machine in different sequences. They set thousands of switches by hand. This process, programming Eniac, could take days for a single new calculation. Once set up, however, Eniac was breathtaking. It could perform 5,000 additions per second. It could multiply two 10-digit numbers in less than 3 milliseconds. Problems that would take a human mathematician weeks were solved in hours. Problems that had simply been impossible before were now merely difficult. Eniac worked using the decimal system rather than the binary system that modern computers use. It stored numbers using rings of 10 vacuum tubes, each ring representing one digit. It was, in this sense, closer to a mechanical calculator than to a modern computer, but infinitely faster than any mechanical device. The machine was divided into units, each with a specific function. The accumulator units did addition and subtraction. A separate unit handled multiplication. Another managed division and square roots. A function table unit stored constants. A master programmer unit controlled the sequence of operations. To run a calculation, engineers connected these units with cables, setting the path that electrical signals would travel through the machine. The result was less like programming and more like constructing a dedicated circuit for each specific problem. It was slow to set up and fast to run. And for the army, that was exactly what was needed. Part 4. The women who ran it. Here is something that history forgot for decades, and has only recently begun to remember. Eniac did not run itself. And the people who programmed it, who figured out how to translate complex mathematical problems into the sequence of cables and switches that would make the machine solve them, were 6 women. Their names were Jean Jennings, Frances Bealers, Betty Snyder, Marlon Westcoff, Ruth Lichterman, and Frances Elizabeth Holberton. They had been working as human computers for the Army, calculating firing tables by hand. When Eniac was built, they were selected to program it. They received no formal training. They were handed blueprints and wiring diagrams and told to figure it out. And they did. Working from the technical drawings alone, they developed techniques for programming Eniac that formed the foundation of computer programming itself. At the famous demonstration in February 1946, it was their work that ran. The journalists photographed them next to the machine but assumed they were models hired for the occasion. Their names were not mentioned in the press releases. For decades, they were largely written out of the history of computing. In recent years, their contributions have finally begun to be recognized. A documentary called The Computers told their story. 3 of them, Jean Jennings Bardick, Frances Elizabeth Holberton, and Betty Snyder Holberton, are now recognized as pioneers of computer programming. They did not just operate Eniac. They invented what it meant to program a computer. Part 5. What Eniac actually did. Eniac arrived too late to help with the war it was built for. By February 1946, World War II had been over for 6 months. The firing tables it was designed to calculate were no longer needed. But Eniac's story was just beginning. Its first real task after the war was not artillery calculations at all. It was a top-secret project connected to the development of the hydrogen bomb, to determine whether a thermonuclear weapon was feasible. The calculations required over 1 million punch cards and took several months to complete. But they would have been simply impossible without Eniac. The machine proved that electronic computing could tackle the hardest problems in science. Eniac went on to be used for weather prediction, cosmic ray studies, wind tunnel design, and a range of scientific calculations that had previously been out of reach. It ran continuously, around the clock, for nearly a decade. In 1947, Eniac was moved from Philadelphia to the Aberdeen Proving Ground in Maryland, where it continued to operate until October 2, 1955. On that day, at 11:45 in the evening, Eniac was switched off for the last time. It had run for 80,000 hours. Part 6. The Legacy. Eniac was not, strictly speaking, the first electronic computing device ever built. That distinction belongs to Colossus, a secret British machine built in 1943 to help crack Nazi codes, and to the Atanasoff Berry computer, built at Iowa State University in the early 1940s. Legal battles over patents would eventually conclude that the ABC predated Eniac's key concepts. But Eniac was the first general-purpose electronic computer, a machine that could be reconfigured to solve different problems. And it was the first to demonstrate publicly, undeniably, that electronic computing was not just possible but transformative. Every computer that followed, from the room-sized mainframes of the 1950s to the chip in your smartphone, descends in some sense from what Mauchly, Eckert, and those 6 programmers built in a basement in Philadelphia. Eniac also taught the engineers who built it something crucial. John von Neumann, working with the Eniac team, developed a new concept for how computers should be designed, one where the program itself would be stored in the machine's memory rather than wired in by hand. This idea, the stored program architecture, became the foundation of virtually every computer ever built since. We still call it the von Neumann architecture today. Your laptop uses it. Your phone uses it. Every server in every data center on Earth uses it. It began with a 30-ton machine that dimmed the lights in Philadelphia. Eniac was built to solve a specific, urgent, military problem. It solved that problem too late to matter for the war. And in doing so, it accidentally changed the course of human history. That is often how the most important inventions work. They are built for one purpose and end up serving another. They are built by people trying to solve today's problem and end up creating tomorrow's world. The 6 women who programmed Eniac could not have known that they were inventing computer programming. Mathematician John von Neumann, who had consulted on Eniac's design, used the machine to run calculations that helped determine whether a thermometers to a device billions of people would carry in their pockets. But they built it anyway. They solved the problems in front of them, one by one, with the tools they had, bit by bit. In the next episode, we go inside that machine, to the vacuum tube itself. What it is, how it works, and why its replacement by something the size of a fingernail changed everything. Subscribe so you don't miss it. And if you found this story worth your time, a like helps this channel more than you might think. Thank you for watching.